Hello, I'm Thomas. I'm a lecturer in applied mathematics here in Leeds, and I want to tell you something about bouncing balls and the analysis of bouncing balls. Now, you probably know about bouncing balls like this one, and that's fairly easy to analyze. If I drop the ball from a certain height, then it will hit the ground at a certain speed, say u. It will bounce back up, it will leave the desk or the ground with a speed v, say, and will reach a certain height again, and then the process continues. If the ball is quite bouncy like this one, then the initial height and the height after the bounce will be very similar. If the ball is not very bouncy at all, then the height after the bounce will be quite a bit lower. Now this is all quite simple and we can analyze this. There are equations for this. Today I want to look at something a little bit more complicated, which is known as the two-ball bounce, and it works as follows. We've got two balls, a bigger one underneath a smaller one, and if I let them drop, then something more interesting happens. And this is what I want to analyze today. I'm not going to show you the experiment, and at the end you will see why. So let me just make a little sketch of this experiment. For the two-ball bounce, well, the starting situation is that we have a small ball on top of a big ball, and both of those balls drop. They will hit the ground and will bounce up again. Now in between these two states, there's a hidden second collision. And this comes as follows. The air or around the lower ball will perturb the fall of the upper ball, and so the balls will separate very, very slightly whilst they're falling down. So in between this state and this state, we have the following situation. We have a situation that the lower ball already hits the ground and bounces upwards, while the small upper ball still falls downwards. In this case, the two balls will approach each other. There will be a second collision, and this second collision leads to a more interesting analysis. That's the end of the introduction. Right. Before I continue with the analysis of the two-ball bounce, I want to tell you a little bit about the general theory about collisions of balls or particles that move in a straight line. So you can see this on the slide now. I want to derive some formulas and some equations, and first of all I need to label my particles or objects. And on the slide I've got two objects that move horizontally. Okay, for the ball bounce they move vertically, but this doesn't really matter for this part. So here I've got two objects, B1 and B2, that move horizontally, and they have velocities u1 and u2. B1 is moving to the right, so its velocity u1 will be positive. The velocity of B2 will be negative and is u2. These balls or objects will collide and then they will move apart again. And I will denote the velocities after the collision by v1 and v2, such as you can see on the lower picture. Now if we want to analyze this collision, what does it mean first of all? Well, one question, especially for the two-ball bounce, is what are v1 and v2? What are the velocities after the collision? We have two physical principles to do this: the conservation of momentum and Newton's law of restitution. So let's have a look at the first one. The conservation of momentum says that the overall momentum in a collision is preserved. Now you probably remember that the momentum, or the linear momentum as it's also called, of an object is the mass of the object multiplied by the velocity of the object when it moves. So we have two objects in our collision, so these objects have both a momentum, and to get the overall momentum we simply form the sum of the two momenta. And then you see the equation on the screen. The product of m1 and u1 plus the product of m2 and u2, which is the momentum before the collision, must be equal to the momentum after the collision, and that is m1 times v1 plus m2 times v2. That's our first equation for the analysis. The second equation comes from Newton's law of restitution, which states that the ratio between the speed of separation and the speed of approach is a constant. Now we have to look at the speed of separation and the speed of approach a bit more carefully, because we've used velocities, and these are sign quantities, so they can be positive or negative. To work out the speed, we have to look carefully at the signs, and if you do this, just look at the first images again, then you see that the speed of separation is given by v2 minus v1, and the speed of approach is given by u1 minus u2. You see, for example, minus u2 is the speed of the second particle before the collision. So this ratio is a constant, usually denoted by E, and E is called the coefficient of restitution. We can easily make sense of this coefficient by just remembering what happened with the one-ball bounce. If the ball reaches very much the same height again as the initial height, this means the speed of separation from the desk is very close to the speed of approach. This would correspond to an E that is very close to 1. In the ideal situation that E is 1, we call this an elastic collision. On the other hand, the other extreme scenario is that E is very small, or even 0. This would correspond to a ball that doesn't bounce at all. For example, one that just sticks on the desk after the bounce. Now, for the two-ball bounce, we will assume that all the collisions are elastic, so we will assume that our balls are quite bouncy. And that's the end of the theory part. Right. So now let us apply the general theory to the problem of the two-ball bounce. I've depicted the situation here. This is the extra collision that we discussed between the lower, bigger ball that already moves upwards and the small ball that still is falling downwards. So I've labeled the balls now similar to what you've seen on the slides. I call the lower ball B1 and its velocity will be U1. I call the upper ball B2 with velocity U2. And like I said, what I want to assume is that the balls are very bouncy and all collisions are elastic. What I want to do is, I want to find out the velocities after the collision of B1 and B2. So what we have to do first is we have to establish the velocities before the collision. Before the collision, what happens with B1? B1 hits the ground at a certain speed, say u. And then we assume that the collision between B1 and the ground is elastic, so it will also come off the ground with the speed u again, which means the velocity u1 will be u. What about B2? Well, B2 is still falling down. Both balls fall together, apart from this instant where they move in opposite directions, so the velocity of B2 will also be u. In fact, it will be minus u because it's pointing downwards. So u2 is minus u. Now we've got the situation before the collision covered, and now we can use the law of restitution and the conservation. Okay. Now we've got the situation before the collision covered, and now we can use the law of restitution and the conservation of momentum to find out about the velocities after the collision. So let us analyze the situation after the collision now. First of all, we can use Newton's law of restitution. This law tells us that the difference of separation is the same as the difference in speed of approach. So we can write this as follows. The velocity of the ball B2 minus the velocity of the ball B1 after the separation is the same as U1 minus U2. Remember that the coefficient of restitution is 1 because we assume elastic collisions. And now we can substitute in the values for U1 and u2 in this equation. u1 is u, u2 is minus u, so u1 minus u2 is 2u. From this equation we see that v2 is v1 plus 2 times u. That's our first equation. Now we have the conservation of momentum. Which reads as usual, m1 times u1 plus m2 times u2 is m1 times v1 plus m2 times v2. Again, I'm using what we have established for u1 and u2. So I can simplify the left-hand side to m1 times u minus m2 times u. And this is still m1 times v1 plus m2 times v2. And now I can use the formula up here and substitute in v1 plus 2 times u for v2. So this is m1 v1 plus m2 times v1 plus 2u. Now it's a good time to recall what I actually want to find out about. I want to find out about the velocities v2 and v1. Here I've got an equation that only contains v1. All the other quantities are known, at least in principle. We know what u is, well, that is some speed, and we know the masses of the particles. So now I simply have to solve this equation for v1. And I'm running out of space. Okay, I want to solve this equation for v1. So let me bring all the terms that don't contain v1 onto the left-hand side. I've got m1 u1, or m1u, sorry, minus m2 times u. And here I've got a 2 times m2 times u. These are all the terms without v1. And on the right-hand side, I've got m1 v1 plus m2 v1. And now I can simply take out v1 here and divide through by m1 plus m2. So I find that v1 is the following. It's m1 times u minus m2 times u minus 2m2 times u are 3 m2 times u, and then I divide through by m1 plus m2. That's the formula for v1. I have a formula for v2 over here, which I can use once I know what v1 is. So that's a very general formula, but now we have to remember that the upper ball is much smaller than the lower ball. So one way to express this is to say that the mass m2 is very, very small, or indeed almost zero. So we can say, let us consider the case where m2 is approximately zero. We have got a very light, small ball. What happens to v1 then? Remember, v1 is the speed of the lower ball after the collision. So then this term is almost zero, right, because m2 is very small. And m1 plus m2, well, that's approximately m1, because m2 again is almost zero. So v1 is approximately m1 times u divided by m1, which is u. And v2, well, that's just v1 plus 2 times u. That's 3 times u. And now you see what the extra collision gives us. The upper ball leaves the collision with a speed that is 3 times as high as it usually were if we only had one ball bouncing. The speed of the upper ball after the collision is 3 times u. Okay, and the lower ball also goes up with the velocity u. So what does it mean for the collision? What does it mean for the bounce? Well, you probably remember from your mechanics lectures that the speed is proportional to the square of the height, which means when the upper ball after the collision has 3 times the speed it usually would have, it will reach a height that is 9 times as high as the initial height. So the 2-ball bounce leads to quite a big bounce of the upper ball. And I've got some numbers here. We, of course, made the assumption that m2 is almost 0. But you can do the whole analysis. You can sub in some numbers for the masses of the 2 balls. If B2 was a tennis ball, then its mass is 57 grams, approximately. If B1, the bigger ball, is a basketball, then its mass is about 600 grams. And when you plug in these numbers for M1 and M2, you find that V2, that's the interesting speed, is not quite 3 times u, because M2 is not 0, but it's 2.65 times u. So for these more realistic numbers, the upper ball would still reach a height that is 7 times as high as the height from which it was dropped. So if you want to do the experiment, you better do it outside.